Good evening, everyone. Welcome back to NPTEL live session for week 8. And today we will be talking about or initiating our topic for cross coupling reactions. So we will wait for a few more minutes for others to join. Thank you so much. Okay, so we can start our session for today. So as I mentioned that we ended up our last session regarding the introduction of coupling reactions. What are the different types of coupling reactions we are going to talk about? So I'll just give you a brief recap about it. So from the last lecture, so we were talking about C coupling reactions, and in that one we talked about Heck reaction. These all coupling reactions we will be discussing in full details along with their mechanism, problems, still coupling, Sono-Bashira coupling, hydrocyanation reaction, and etc. So basically, we found out that generally in these reactions, we will be talking about mainly palladium-based metal catalyst because it is having low toxicity compared to the other 4D5D systems. Also, it can tolerate a variety of functional groups. This is most commonly used catalyst with for CC coupling reactions. Most commonly used. Okay, so now we were talking about from the last session, we were talking about that what is the difference between the catalytic and the cyclomatic fashion. We will not go into the details again. So we will start our first topic of the discussion, that is CC, carbon-carbon cross coupling reactions. And specifically in that one, allylic alkylation. That means at an allylic position, you are doing an alkylation, you are introducing an alkyl group. So we have generally seen that CC coupling occurs well at alpha position, but at allylic position, not much of the study is being done. So it has been overlooked many a times. So we can consider what is an allylic bond, for example. So you have, so this basically, when three atoms are involved in this particular position is your allylic position, and there you, this is your basically this is your group and this is your alpha position. So this is called an alpha carbonyl. And when I am converting it to R, so this becomes an alpha carbonyl alkylation because this is your group, this one is your group, and adjacent to that one is your alpha position here, and here you are introducing your alkyl group, and this is called alpha carbonyl alkylation. Similarly, if I have an allylic position, so this is your allylic position, and here we want to introduce an alkyl group. So what would happen? It would be replaced by R. Now this is called as allylic alkylation, right? So how this occurs and what is the mechanism? So we will look into that one. So we will be talking about mechanism of allylic alkylation, the general mechanism that would help you to understand and solve problems wherever you will see an allylic alkylation process which is likely to be happening. So as I mentioned that we will be using a palladium catalyst. Here palladium catalyst is being used. So first of all, we have a square planar palladium complex, and that loses its two ligands, forms palladium L2. Now the first part of the reaction is when we are introducing and some allylic group where X is a leaving group, and now it has to be introduced into your system because at this position only you will be putting up your R group. So to introduce in this position, this process is called as oxidative addition, OA. So what your structure will now look like, the allylic bond and the X will bind with your palladium, and the other two ligands will go in a transposition. Followed by that, now since here we have, if you will see here, it is eta 1 allylic. Now it would undergo to, and this is sigma, so it will undergo sigma to pi rearrangement. That means it goes from eta 2, eta 1 to eta 3 and forms. When it is going to involve eta 3, that means this leaving group will go out and that would have your allylic bond over here, giving a positive charge, overall positive charge to the complex, and X is the leaving group which would go out and make as form as an anion. Now followed by when this is having a positive charge and there is a possibility of the nucleophile to come and attack now. So what would happen now? Your nucleophile will come and this will enter now. When this is entering, what really will happen? Right? So what would happen? This is going to give out your product, which is this nucleophile can go and attack onto one of the positions of the alkyl and it would cleave out the group forming and nucleophile with halogen going out and then for reforming the palladium L2. And when it is being given 2L again, the two ligands, it would reform your catalyst, which is palladium L4. So this has been given by Shuji in 1986. So this is the general mechanism of your allylic alkylation, where what we have seen so far is you have a palladium catalyst, which will firstly lose out its two ligands. It would form palladium L2. Now, when palladium can accommodate two more sites or groups because it is having that vacant coordination around it. So this particular group, which is our substrate, it would, you can call it as a breaking of the bond. And one of the part will attach at one side, another part will attach at the other side. This is actually an oxidative addition reaction. So basically your palladium will donate two electrons, one to each, and therefore they form a bond with the palladium. And palladium will go from its, say for example, if it is in N oxidation state earlier, after the oxidative addition step, it would become N plus 2. So this is your oxidative addition step and where your palladium will lose two electrons. Your metal center will lose two electrons, followed by when we have an allylic bond, which is in eta 1 form, sigma 1, and now we want to remove this particular X, it would rearrange from eta 1 to eta 3, followed by the leaving of your X group, which is a leaving group. It can be halogen, it can be anything. Once this rearranged group or complex has been formed, now palladium has attained a positive charge or overall positive charge is there on the complex. Nucleophile will come and target one of the position of your alkylic bond. It would leave out the product. So this was a product that we were talking about and release your palladium L2. This palladium L2 will take up the two ligands which has been lost earlier and re-giving your catalyst back. So this is the general mechanism of your allylic alkylation. Those who have missed what is an allylic alkylation, generally at an allylic position, if you are removing your proton and any allyl group or a nucleophile is coming and attacking at that position. So this is called as allylic alkylation. So there are certain points that we need to keep in mind when we are doing an allylic alkylation. So, we have allylic alkylation. Basically, we are talking about the ratio selectivity. At what position you're going to get a product, major product. So as I mentioned that at this particular step, nucleophile is going to attack. And if I am having, say for example, nucleophile is having two possibilities to attack at your allylic site from where it would prefer to attack. So nucleophile always prefer to attack from the less hindered side. which means hindered side of the eta 3 allyl ligand, including there would be some electronic effect also, which you can consider coming from the catalyst, right? So wherever if your allylic position is having at one side it is having more hindrance and other side it is having less hindrance. So nucleophile will always come from the side where there is less hindrance. That means like wherever it is getting more space to come from, it would enter from that side. Second point for this mechanism was the tendency of the leaving group is very, very important over here. So it has been considered. And how it has been considered? So if you have chlorine, the ester group, the acetate group, so what would be the tendency of the leaving group? Firstly, if you have these four leaving groups, chlorine would be the first one to go out, followed by this, and at last the OH. So this is a comparative data where they have set up the reactions and performed and what are the rates being calculated. Based on that, the trend has been given. And this has been formulated by Beckwell in 1992. So let's see one of the reactions which follows is allylic alkylation. So now we are taking one example of asymmetric allylic alkylation. Asymmetric meaning wherever you will be end up having some chirality in your system, there you will specify your asymmetric reactions. So firstly, I will talk about the group, and here is the other group. Double bond, and here it is phenyl. Here it is our group having an H as well. And we will be including a chiral palladium catalyst, which will be having two sites vacant in presence of a base and solvent. So what do we expect? What it would form over here? So what is your allylic position? So we have this bond, and here this is your allylic position. And at this position, we want our this group to be attached. And what is the possibility of having that one? That means this would act as your nucleophile, and this is your allylic substrate. And since we are using a base, if you go by a proper mechanism, your base can take up the proton. Once proton is gone, it would generate a negative charge onto your this substrate, followed by formation of this moiety. When this negative charge is there, that is acting as your nucleophile. And as I mentioned, this whole group you can consider as a allylic bond, where R, this is your X. In this particular earlier case, when I was mentioning that here we were having double bonded and we were having X. Instead of X, now here it is, we are having an acetate group, as we were mentioning, and this will participate. And what we expect to have it over here, the final product that we will be having would be your at this position, you will make a bond with the nucleophile, double bonded O, nitrogen, double bonded phenyl group, and here it would be proton. So this is your product, followed by the rearrangements. It can, or further reaction, it can also make a group like this way, where you have NH3 and CO2. So this is one such example. Now moving towards your next coupling reaction, which is Heck reaction. So in Heck reaction, what we have in hand is the replacement of a vinylic. Early reaction, we saw that allylic retaliation. Now here, the vinylic proton would be replaced by either vinyl group, benzyl group, or any aryl group. Say, for example, we have is, so this is your vinylic sites, CO2Me, in presence of base at 100 degrees Celsius using 1% palladium acetate and 2% PPH3. What you end up having, you will make a bond between this and this position, because this is the one which is going to go out, and you will end up having CO2Me. Let's check the mechanism. Heck reaction mechanism. So here, as I mentioned, we were using palladium acetate. It's a +2 oxidation state. It would convert to palladium 0, where it is using a phosphine, where your L is PPH3 in presence of base. Now, first step would be introduction of your R-X, where it would form palladium L, L, X, and R dash. Now you're introducing your vinylic group. Now at this position, this R dash is going to substitute at certain place. How it would form? It would enter from a less hindered site, which is this one. So this is your less hindered site. And therefore, what you will end up having will form R here, R dash here. This is H, this is H, right? Followed by your next step would be to release your product, which is R dash double bonded R, and forming palladium X, L, L, and H. Now at this point, you're introducing your base NET3, which would take out your proton and halogen, giving out palladium L2, which can reform to palladium acetate if we introduce the acetate back again. So this is the mechanism that is being followed for the Heck reaction. There are certain generalized points for Heck reaction, which will be take up now. First point that we have is the oxidative first step. The steps that are being followed for the Heck reaction. First step is oxidative addition of your R-X to the palladium 0, giving trans complex R dash palladium L2 and X. The second point, to avoid, because there would be a chances of rapid beta elimination if your R dash group is other than that of, or meaning it should primarily be vinyl, benzyl, or aryl group. Third point is, or we can call it as a, this is just a note. This is not your, this is step 1. Step 2 is insertion. Once that is done, then olefin will be inserted into the palladium carbon bond of trans Rx palladium L2X, followed by, once that has happened, there would be a beta elimination, because as and when olefin gets inserted, there would be a formation of some interaction between the olefin and that R group. With respect to that, beta elimination will give the substituted product olefin. And at last, we have a step 4, which says that your regeneration of the catalyst by reaction with base ET3N. So these are the steps that have been followed for Heck reaction. Now, there are certain electrochemical investigation for Heck reaction that also we will look into. Electrochemical investigation. So which suggested that participation of the anionic palladium species in the catalytic cycle. So this has been said that so it says that this investigation suggests the participation of anionic palladium species in the catalytic cycle. We have two ligand, palladium acetate, loses two electron to the A1 acetate, and two electrons are there, forms OAC, minus is outside. When introduced R-X, it forms palladium X O acetate minus. So from this we get to know that here it is emphasizing the entrance of anions in the rate of oxidative addition in the catalytic cycle. Followed by, so this was about the electrochemical investigation that they mentioned about the anionic nature of the palladium complex, which is necessary for the catalytic cycle. Now we will talk about the insertion step of Heck reaction. So this happens in a concerted pathway. So we have a palladium, say R and two other coordination, and we have an alkene. Bonds are out of the plane. Now, what would start happening? Would start interacting with R group, iridium, forming a bond and breaking of this bond. This is a double bond which is breaking now. So this is your transition state. Now what would happen? That this bond would be breaking up and here it is going to form. So we end up having palladium. We can make it in the slide. Palladium here. We said that new R bond would be formed. And here, so this is the way we end up having an insertion step of the Heck reaction. Now let's see another example of Heck reaction, which is the arylation of styrene. So we can replace the vinylic proton by either vinyl group or aryl group or the benzyl group. So here we are doing the arylation of the styrene. So what we are starting here with, so we have a complex DPPE, vinyl. There is already phenyl annex, and this is our vinylic substrate. Now here at the vinylic position, because this is already hindered, at this position we will be having our, if the hindered position has been acted, it would form, otherwise it would form a trans PPH like this way. So there are certain conditions. Which at what conditions PP, pH and pH is forming like this. pH and pH. So it depends upon a lot of roles, which is your leaving group X, your solvent, and this is A, this is B. A percentage formation, product formation of B. So if I have a triplet ion and I'm using a solvent which is DMF is to water as 9:1. These are all the experimental conditions that has been tried to follow this reaction. So they found in this condition 42% of your first A is being formed and 58 of B. If you change the anion to PF6 minus and only use DMF solvent, it forms 43 and 47, 57. Then iodide in DMF, it forms 20:80, followed by the change to triplet in THF formed 8:92. So the stable product has been formed in the last condition. We also have in Heck reaction the regioselectivity. So at what step you will see the regioselectivity happening. So if we have palladium, where the one side it is having ligand. And here is the group which is attached after the insertion step. R2, this is R3, and this is R4. So here we have a proton, and there is a possibility of beta hydride. this this is your alpha, now this is your beta, and this is your beta dash. Now there is a possibility of first the beta elimination, where you will end up having a product type R4, and double bond is being formed here, R1 and R2. Or if you have beta dash elimination, you would end up having double bond here, R1 and R2. So these are the possibilities where your competing beta elimination can end up, or the one that reaches selectivity of your Heck reaction. So this was all about the Heck reaction, where we saw the vinylic proton to be replaced by any vinyl group or aryl group or benzyl group, where the palladium is being used as a palladium catalyst. And we have seen the reaches selectivity, the insertion step, and various other parameters which define the product of your reaction. Now we are moving to the Suzuki reaction. So here also palladium is being used as most of the scenarios. And the important point here is that it uses a boronic acid as a coupling partner. With either alkynyl, alkynyl, or aryl halide. So these are the different substrates that it can couple with. Let's see one such reactions. So we have R boron OH2, R dash X, where we are using a palladium 0 in presence of base. It would end up forming R dash CC coupling, giving out BXOH twice. Let's see the mechanism. Of Suzuki reaction. So here we are starting with palladium L4 I'm taking, which can either lose 2L, making a palladium L2. Now firstly, it would insert Rx, so that would rearrange as in transform. Then at this position, X has to be removed, which is being taken by your R dash BOH2 base. So basically your BH twice R dash, when it has been treated with base, it will form this one. It would give your R dash to your palladium and take the X minus. So ultimately it would leave X BOH whole twice base minus, and it would form R palladium R dash L and L. Now at this position, it has to be a cis trans rearrangement, trans to cis rearrangement, and it would form R palladium R dash L and L, and this group can leave out as your final product and would form palladium L2, which is your catalyst. So here are some things which need to be noted, that here R can be allyl, benzyl, aryl, alkynyl, or alkynyl, right? And your X is, if iodine is greater than triflate, then bromine and greater than Cl. So this you need to keep in mind. And base can be your NaOH, NaOT, phosphate, etc. So here some points for this reaction. First is about the boronic acid. That these acids, they are stable, they are easy to handle, water and thermostable. Second, the cauterization of boron leading to its negative charge is very necessary by using bases to form boronate anions. And the last, that once it is forming a boronate anion, they act as carbanion transfer agents. For making it more understandable, you saw that firstly it was having Rx BOH2. Nowhere at this stage it can transfer the R dash. So firstly, in presence of the base, it forms a boronate anion, giving it BOH2 base and leading a minus charge onto this one. This minus charge has been taken by the R dash. Therefore, uh, it makes as a carbanion transfer agents. You can understand it like a borohydride. When borohydride is there, H minus will transfer. Here, R minus carbon ion would be transferring. That's where your boronate ions become very important. So cauterization is important. So if we talk about the Suzuki mechanism, so the first point, that cycle will start with the oxidative addition, followed by transmetallation, then trans cis rearrangement, and at last reductive elimination. Okay. We have some advantages also. These are very important points that we need to keep in mind, even though it's theory, but it is important. So it has a substrate tolerance, wide variety of substrate tolerance, meaning in presence of OH, NH, CO, NO2, CN, etc., the reaction will work through. It's having low toxicity of the reagents as you're using a boronic acid, which has certain medicinal value as well. Gives a high selectivity of your cross coupling products, and it is economical if you compare the catalyst to rhodium and iridium. So here is one important topic, which is the preparation of organoboron reagent. So it's basically a metaphysis reaction. Here you have a RLi, you have a isoproxide. It would form Li positive, giving you RB PRO3. And when it is being hydrolyzed, acidic hydrolyzed, it would release your lithium positive, it would release isopropanol and would form IPRO2. So where your R can be alkyl, aryl, 1-alkenyl, or 1-alkanyl, like ene or ion bond. As we were mentioning, the advantages of Suzuki reaction, which I said is functional group tolerance. So it's a functional group, which is Fg. So if I'm having here we have Br and a substituted boronic acid, NO2. At this point, we know that this is your aryl bromide and this is your boronic substrate, which is your coupling partner. And there is a lot of like ketonic group, there is a nitrate group. Nothing is going to happen to these functional groups because it is having a tolerance. This is happening in presence of PPH3, palladium, in base, sodium carbonate, benzene, solvent, and refluxing, which would end up giving you a bond between these two aryl moieties having functional group with a 73% yield.